Hello, I'm just going to go through some calculus problem examples from sheet 4. So I'll start with question 1, part 7. So there's the function I've been given, and I'm asked to find any local maxima, local minima, or points of inflection. So the first thing we'll need to do is differentiate the function. We have y, we get dy dx by differentiating with respect to x. So I'll put that a quarter out in front, right? And we differentiate x to the power of 4, we get 4 times x to the power of 3. Then we have minus 4 over 3. Now differentiate x cubed and you get 3 times x squared plus 2. Differentiate x squared and you get 2 times x. Differentiate 1 and you get 0. So I'll just tidy this up. Those 4's cancel, we get x cubed. Those 3's cancel, we get minus 4x squared, and we get plus 4 times x at the end. Now I'll go ahead right away and get the second derivative, d2y dx squared, the second derivative of y with respect to x. And I get that by just differentiating that expression again. So I get 3 times x squared from x cubed, 2 times minus 4 is minus 8, times x to the power of 1, which is just x. And I get plus 4 times x to the 0 is 1, so it's just 4. So I have the first and second derivative. So the first thing I will look for is stationary points. So that is points where dy dx, the first derivative, is equal to 0. So I'll write that down. X cubed minus 4x squared plus 4x is equal to 0. And I solve that for x, and that will give me my stationary points. So first thing I see here is I can take out a factor of x and get x squared minus 4x plus 4, all that times x is equal to 0. I'm going to factorize this again now. So I get that from the first line. I'm going to break up what's in those brackets into two factors. So what we're solving a quadratic equation now, essentially. So I have x squared minus 4x plus 4. So the two factors are going to be x plus something and x plus something else, plus or minus. So if you remember your quadratic equations, my two numbers here that I put in, they're going to have to multiply together to make 4 and add together to make minus 4. So the two numbers I need are minus 2 and another minus 2. So you'll see if I multiply out the two brackets there, I'll get what's above them. I'll get x squared. The minus 2 times minus 2 will give me a plus 4. And then minus 2 times x and another minus 2 times x gives me minus 4x. So I'm nearly done now for stationary points. So if all that is equal to 0, that's three things multiplied together. So if that's equal to 0, it means that either x is equal to 0 or x minus 2 is equal to 0. So I'll have two solutions. X minus 2 is 0 means that x is equal to 2. So I have two stationary points, one at x equal to 0 and one at x equal to 2. So next I'll see what the y values are there. So x equal to 0 means that y is equal to, well, if I pop 0 into that, I get 0 over 4 minus 4 times 0 over 3 plus 2 times 0 minus 1. So it all in the end comes out to be minus 1. For x equal to 2, I get y is equal to 2 to the 4 divided by 4 minus 4 times 2 cubed divided by 3 plus 2 times 2 squared minus 1. So that's equal to 1/3 in the end. So my two stationary points are at 0, minus 1 and at 2, 1/3. So those are the x and y coordinates of my two stationary points. Next I want to see, are these local maxima, local minima, or stationary points of inflection? And to do that I need the second derivative test. There's my second derivative, so I'm going to check if that's positive or negative or 0 at my stationary points. So the first one I'll check the second derivative, d2y dx squared, at the point x is equal to 0. If you remember, was my first stationary point. So that's equal to 3 times 0 minus 8 times 0 plus 4 is equal to 4. Now that is greater than 0. So if the second derivative is greater than 0, that means that that stationary point must be a local minimum. Next I'll check my other stationary point at x is equal to 2. So the second derivative at x equal to 2 is equal to, I'll just pop 2 in there, 3 times 2 squared minus 8 times 2 plus 4. So that's equal to 3 times 4 is 12 minus 16 plus 4 is equal to 0. It looks like we have a stationary point of inflection. Remember that a point of inflection is somewhere where the second derivative changes from being positive to negative or vice versa. So it will be 0 at the actual point of inflection. So there's several possibilities we can have. Remember that a positive second derivative looks like this, and a negative second derivative looks like this. So a point of inflection where we switch, let's say from negative to positive, or from positive to negative, would look like that. Now, a stationary point of inflection in particular, as opposed to an ordinary point of inflection, is one where the first derivative also goes to 0 at the point of inflection. So that is a stationary point of inflection, whereas that would be an ordinary point of inflection, where the first derivative doesn't go to 0 here. So we have 0 first and second derivative on this problem, and now I'm going to check that it is actually a stationary point of inflection by making sure that the second derivative actually changes sign when I go through here. So what I'll do is I'll check the second derivative at 2 points either side of what I think is a stationary point of inflection. So I'll check it first at x equal to 1. Make sure I'm not going to go too far, so I'm not going to go past the other stationary point at x equal to 0, but I'll just check it here. And I'll get 3 times 1 minus 8 times 1 plus 4. That's equal to minus 1. So that's less than 0. And I'll also check on the other side at x equal to 3. So that's equal to 3 times 3 squared minus 8 times 3 plus 4 is equal to 7. So now I have that at the point at x equal to 2, we have 0 first derivative, 0 second derivative, and the second derivative changes sign. So that means we have a stationary point of inflection. And that's both of our stationary points accounted for. So that's all of the maxima, minima, and stationary points of inflection that there are. There's one minimum, local minimum, and there's one stationary point of inflection. The last thing we must check for is ordinary points of inflection. So that's where the second derivative is 0, but the first derivative is not 0. So we'll check for that last. So we find stationary points of inflection by letting the second derivative equal to 0. So we do that and we solve this equation for x. So again we have to factorize this expression. And I actually already know that x is equal to 2 is one of them. So I'll put x equal to minus 2 here first and see what I get, because that will give me an x equal to 2. So whatever I put in here on the right, it's going to have to make 4 with that minus 2. So I think it's going to have to be another minus 2. And let's see what that gets us. So 3x times x gives me my 3x squared. 3x times minus 2 gives me minus 6x, and the minus 2 times x gives me minus 8x. So if I multiply that all out, I actually do get my expression back. So that is a solution, or that is a factorization of that expression above. So now I know that 3x minus 2 is equal to 0, or x minus 2 is equal to 0. So that means my two solutions are I have 3x equal to 2, or x is equal to 2/3, or I have that x is equal to 2. Now I've already checked that one, x equal to 2. I know that's a stationary point of inflection from before. So that means that this other point then, so this new point of inflection at x equal to 2/3, that must be an ordinary point of inflection, because there are no other stationary points. So we know there's not one at 2/3. I'll just check that it is actually a point of inflection by checking that the second derivative changes sign as we go through that point. So I'll check on the right side of it first, and I see from before I know that at x equal to 1 the second derivative is minus 1, which is less than 0. I also know that at x equal to 0 the second derivative is 4, which is positive. I had that as well from the previous part. So if I draw a little diagram, on the left side of 2/3, or x equals 2/3, I have positive second derivative. On the right side I have negative second derivative, and I know that the second derivative is just equal to 0 right at that point, at the point of inflection. So because the second derivative is equal to 0 and changes sign, I know that that point there at x equal to 2/3 is an ordinary point of inflection. And I just finally would say that at x equal to 2/3, y, if I pop it into the formula, will equal to, well, it comes out to be something like minus 0.45679 roughly. So I can say that that point then is an ordinary point of inflection. And now we've dealt with all the points where the first or second derivative are 0, so that's all of the stationary points, maxima, local minima, and all of the points of inflection where the second derivative is 0. That is about as hard a question like that as they get.